Moving on from attention methods in deep learning models and transformers, we will now move to 2 weeks of a contemporary topic in deep learning, which is deep generative models. Deep generative models includes topics such as GANs, generative adversarial networks, and variational autoencoders, VAEs, which have been extremely successful over the last few years. Before we talk about overall perspective of deep generative models, let's talk about the landscape of machine learning itself and try to understand where deep generative models fit into the scheme of machine learning methods. If you considered supervised learning is about learning a mapping between inputs and outputs, that is data and class labels. Your data is typically given in the form of input label pairs such as x1, y1, x2, y2, and so on and so forth till xn, yn. And the goal of a machine learning algorithm is to learn a model that can map x to y. So it aims to learn a function f, which when applied on x gives us y, where we'd like y to be as close to the original ground truth y that's provided. So what are the supervised learning settings or problems that we have seen so far? In computer vision, we have seen problems including classification, localization with classification, detection, segmentation, so on and so forth, all of which are supervised learning problems where there was an expected output for a given data point, and our deep neural network was trying to learn that function that takes you from input to output. The nature of the output varied with different kinds of tasks. For detection, the output looks different from the output for classification, and for segmentation, the output looks different from that of detection and classification. That resulted in different kinds of architectures, loss functions, and so on and so forth. So what are we talking about here to go beyond supervised learning? So if we think about paradigms beyond supervised learning, we talk about unsupervised learning, where the broad goal is about just understanding data. Another setting is about detecting outliers. That's another setting where one can use unsupervised learning. And finally, the focus of this week's lectures, which is generating data from past data. No labels involved as it is, but just generating data. So if you considered just unsupervised learning, which is perhaps the most popular form of going beyond supervised learning, the main idea is to capture the underlying structure of the data. You are given only the data, there are no labels, and since no labels are required, often training data is cheap to obtain. The most difficult part often can be to get annotations or labels for data, which depending on domains can be challenging tasks. For example, in healthcare or genomics or bioinformatics, trying to get labels for a data point may require experts to participate and may be a very costly affair, both time-wise and money-wise. Unsupervised learning is generally categorized into clustering methods such as k-means clustering, dbScan, so on and so forth, and dimensionality reduction methods such as principal component analysis, isomap, and many other such methods. The focus of this week's lectures, as I just mentioned, is generative models, which is another variant of unsupervised learning, where the goal is, given a set of data points, our objective is to generate more data samples similar to the ones in the training set. What does that mean? Given a set of data points as you see here, so those are points that lie on some manifold. Remember that manifold corresponds to a locally Euclidean surface, which you can look at as the intrinsic dimensionality of your data. So if data lies on a certain manifold, which corresponds to a distribution, we learn using some method a model, which can then sample from a distribution that the model has learnt and generate new data points. What does this mean mathematically? If you had training data x1 to xn, which comes from some underlying distribution, let's say P sub d, and we'd like a generative model to sample data from a distribution P sub m of x in such a way that we minimize some notion of distance between PD and PM. We'd like to learn PM in such a way that PM becomes close to PD in some notion of a distance. How do you do this? Can we elaborate on this? Let's try to go a bit further. So we said we'd like to minimize some notion of a distance between PD and PM. Given a data set from an underlying distribution PD, consider an approximating distribution PM coming from a family of distributions M. Our objective is to find that parameterization in M or that distribution in M given by theta, the parameters of that distribution is theta, which minimizes some notion of distance between PM and PD. So the objective function will be theta star, that's our solution, is given by argmin theta over M, distance, some distance function of P theta and PD. What distance function do we use? If we choose KL divergence as the distance function, recall that KL divergence is a loose distance function between two probability distributions. It does not satisfy all properties of a distance metric, but it's commonly used to measure the distance between two probability distributions. If we replace this distance function by KL divergence, it can be shown that the above problem becomes one of maximum likelihood estimation. Theta star becomes argmin over theta belonging to M, expectation with data points drawn from the distribution PD minus log P theta of x. This is maximum likelihood estimation or minimization of negative log likelihood. Why is this so? We're going to leave that as homework. It's fairly trivial to show that if you replace distance with KL divergence, you will automatically lead in 2 steps to negative log likelihood. But please do work it out and we'll discuss in the next class. This idea of learning PM or P theta in this case using maximum likelihood estimation is one way of learning generative models or deep generative models in our case. A set of methods called pixel CNN and pixel RNN very explicitly use this as the objective to learn deep generative models, and we will see these methods a little later this week. What are the applications? Why should we learn deep generative models? Deep generative models can be used for image super resolution. Given an input image which is of low resolution, you can use generative adversarial networks or any other deep generative model to learn a super resolved version or a high resolution version of the original image. You could use such models to colorize images, go from sketches to color images, or go from black and white to color images. You could use this for cross-domain image translation to go from one domain to the other. In this case, we talk about taking a picture of a zebra and going to a picture of a horse. But you can also talk about going from a picture to a cartoon and so on and so forth. And finally, you can also talk about generating realistic face data sets for performing face recognition and so on and so forth. There are many more applications. The goal can also be just to learn good generalizable latent features. By learning to generate new images, the model also allows you to learn latent representations, which by we mean the hidden representations in certain layers of that model, which can then be used for other downstream tasks such as, say, classification. You can also use this generation of new data to augment small data sets so that you can then get more larger data sets which you can train for downstream tasks such as classification again. You can use such models for enabling mixed reality applications such as virtual try-on. You can imagine now going to any shopping website and let's say you'd like to try on a shirt or a trouser before you purchase it. You could now take your image and see how you'd look in that particular shirt or how you'd look with a specific kind of glasses or sunglasses for that matter. Many more applications that we'll see this week as well as in next week's lectures. Before we move on with methods for generative models, what do generative models really mean? Let's try to understand this from a conceptual perspective. Generative models can be distinguished from its complement, which are known as discriminative models. In machine learning, discriminative models aim to learn differentiating features between different classes in a dataset, whereas generative models aim to learn the underlying distribution of each class in a dataset. Note here that we are now trying to use an example from supervised learning to understand generative models better. For all the examples that we saw so far of generative models as unsupervised learning, generative models can also be used in supervised settings where you can specify the class label and the model will generate data from that specific class. So for example, if you're generating a face image, you can say which person you want and the model can generate the face image for that person, which would correlate to a more supervised setting than an unsupervised setting. So in discriminative models in supervised learning, the goal is to learn a discriminator that separates two classes. Example would be support vector machines, which is a maximum margin classifier. On the other hand, in a generative model, the goal is to learn the parameterizations of distributions for each class. In a discriminative model, one would finally do inference by asking if a test data point belonged to one side of a hyperplane or the other side. If it fell on one side of the hyperplane, you would say it belongs to class +1, and if it belongs to the other side of the hyperplane, you would say it belongs to class -1. Now, in a generative model, what we try to do is to find out what is the given a data point, what is the probability that the distribution of class +1 generated this data point, and then we'll try to find out for the same data point what is the probability that the distribution of class -1 generated the same data point. You can see here that the entire approach to assigning a class label for the new point is generative and tries to understand how likely would a certain distribution would have had a probability of generating a particular data point. That's the difference between discriminative and generative models more broadly in machine learning. So to discuss this further, if you considered a binary classification problem of classifying, say, images consisting of ones and zeros, a discriminative classifier tries to model the posterior P of y given x, which is a conditional distribution, where x is given as input and your model has to give a particular probability for y given x. So discriminative classifiers model this conditional distribution called the posterior. On the other hand, generative models model the joint distribution P of xy. So how would you use a generative model for giving a class label or assigning a class label? You would take a test data point, use this joint distribution to find out if this data point was assigned a class label +1, what is the probability of having generated such a data point? If this data point was allotted a class label -1, what is the probability of having generated such a data point? And that would give you a way of getting a class label from this joint distribution. Remember that posterior, the conditional distribution, and joint distribution are related from your basics of probability, where P of y given x is P of xy, your joint, by P of x, which relates to the Bayes theorem, which states P of y given x is equal to P of x given y into P of y by P of x. Some of these understandings is something that we will use when we talk about different deep generative models. Existing deep generative models can very broadly be divided into two kinds. One, known as fully visible models. These fully visible models directly try to model the observations. You can see here the observations are x, and the model tries to capture these observations themselves without introducing any extra random variables. So the only random variables considered are the x's or the data that you have. So for example, you could be considering each pixel value of an image as an observation, and now based on that you learn a generative model which can generate new images. The other category of methods are known as latent variable models, where you introduce other kinds of random variables known as latent variables or hidden variables, which we assume generate the data, which we try to learn as part of generating the latent, as part of learning the generative model. Within these kinds of models, latent variable models, there are, very broadly speaking, two kinds: explicit and implicit models. In explicit models, we try to explicitly define and learn a certain likelihood of data by defining a certain distribution. We may, for example, define a Gaussian on data or a mixture of Gaussians on data, and then try to learn the means and covariances of those Gaussians as part of the learning procedure. On the other hand, in implicit models, there is no distribution assumed, there is no probability density function parameterization that's assumed. Given a set of data points, we do have some latent variables, but we'd like to learn the latent variables in such a way that we can generate data points that look similar to the data points that we have in our training data. We don't impose any specific distribution on distribution form on any of these on any of the data or the model's distribution in this particular case. More generally speaking, there's an entire taxonomy of dividing existing approaches for coming up with generative models. So as we just said, very broadly speaking, generative models can be divided into explicit methods and implicit methods, where in explicit methods, you assume a certain PDF density function and try to learn the parameterization. And in an implicit function, we don't assume any such distribution, but we just want to learn a certain density function which can generate data that looks similar to what we have seen in our original training data. Within implicit density generative models, a popular example are GANs, generative adversarial networks, which directly try to use the implicit density learnt and generate data points. Another variant of implicit generative models are Markov chain based models such as generative stochastic networks. These are not as popular as GANs these days, but that's where they fit into the overall landscape of generative models. On the other hand, within explicit density generative models, you again have two kinds. One, where the density is tractable and you can estimate it and move forward to generate data points. Examples of methods here include autoregressive models, NAID, MAID, NICE, GLOW, Fjord, so on and so forth. We'll at least see some of these in later lectures this week. Another kind is where you do have an explicit density function, but you cannot directly compute it, and you compute it through an approximation, where the most popular method is through a method known as variational inference, which leads to a model called variational autoencoder. Another approach here is also again using Markov chains to approximate this density function, which leads to a family of methods known as Boltzmann machines. We won't cover all of these methods in the lectures, but cover the most popular ones, including GANs, VAEs, and some of these tractable density methods. For more information, you can go through this excellent tutorial on deep generative models by Aditya and Stefano, which was delivered at ICHCAI of 2018. And if you'd like to go further, another tutorial in a conference called UAI in 2017 by Shakir and Danilo. Let's revisit one question that we left behind, which was, why does using KL divergence in finding the generative model simplify to maximum likelihood estimation? As I already mentioned, it's a very simple derivation. Please do work it out and try it before we discuss.